Okay, good afternoon. There's two more topics left in diodes, and then we'll turn attention to transistors, three-terminal devices. So there's diode clipper circuits and diode clamper circuits. There are two of the other most popular applications for diodes. So we're going to look at those. And just FYI, similar problem could appear on the final exam. Okay, so we have these diode clipper circuits. And usually what I like to do is I like to use the ideal diode model to explain the operation of these kind of circuits. So here we have a diode series with a resistor, outputs taken directly across the diode, right? We've seen a variation of this. If you take the output across the resistor, what kind of circuit do you have? Nobody remembers? A half-wave rectifier, absolutely. So you apply a sine wave at the input to a series combination of a resistor and a diode. You take the output across the resistor, it's a half-wave rectifier. And the output of a half-wave rectifier is also clipped. Okay, the output of a half-wave rectifier is also clipped. So half-wave rectifier is a clipper circuit. So we did lab 4 last week. No, not last week, the week before that. So we had the half-wave rectifier, the full wave bridge rectifier, then we did the diode clipper and the diode clamper circuits. If you'll notice, half-wave rectifier was the exact same circuit as a diode clipper. Yes. So that's I was just talking about. So what if you take the output across the V out? Where have we seen that circuit before? It's a half-wave rectifier. It's a clipper circuit. It also could be a clipper circuit across the resistor also. So half-wave rectifier is a clipper circuit because it's clipping the negative half cycle, right? So quick and easy way to analyze this circuit, it's let's say in the positive half cycle. The diode is forward bias. So it behaves like a short circuit, right? So what is V out? Positive half cycle is like this. What is V out? If you're trying to measure voltage at the exact same node, what is your V out? 0 volts. So positive half cycle, V out is 0. In the negative half cycle, diode is open. Because it's reverse bias, it's a V out is equal to V in. So V out is equal to V in. What kind of clipper is this? Positive clipper or negative clipper? Which half cycle is it cutting? What kind of clipper is it? Positive clipper, yes. All right, so it's a positive clipper. So the next question I would ask is, what do you do if you want a negative clipper? Just flip the diode. Yep. That's what we had in the half-wave rectifier, right? In the half-wave rectifier, we had a diode that was pointing towards the right, and so it was clipping the negative half cycle. In that same circuit, if you reversed the position of the diode or flipped the position of the diode, it would have flipped the positive half, and you would have gotten a positive clipper. So same circuit, different outputs simply by flipping the position of the diode and simply by changing where you take the output from. Okay, if you take the output across the resistor, what kind of clipper do you have? Think on it. So you can draw it out and think on it. You asking me or you telling me? You don't have to be that impactful. So one answer is positive clipper, but you're saying it's going to clip the positive cycle, the positive clipper, or is it a negative clipper? No, I'm saying the same circuit, but we take V out across that resistor. You sure? You just said positive clipper. Now you're changing your answer? Okay. All right. Should we lock in the answer? How about the rest of you? What do you think? It is the exact same circuit as we saw. It's a half-wave rectifier. The positive half cycle going, except we simply rearrange the resistor the other way around. Okay. This circuit is the exact same circuit we did in the lab. Okay. Except the output is across the resistor in the lab. Here we're taking the output across the diode. Plus, in the lab, the half-wave rectifier, the diode came first and the resistor was drawn afterwards. But electrically speaking, this is something fundamental. Electrically speaking, in a series connection, it does not matter which one comes first. In a diagram, just visually, we think resistor comes first and the diode comes next. But electrically speaking, it does not really matter. Does everyone understand what I'm trying to say? Right? In the lab, then they did the half-wave rectifier. You had a circuit, you applied an input from the left, you had a diode as the first component, then you had the resistor, and you took the output across the resistor. But electrically speaking, whether the diode comes first or the resistor comes first does not matter. Yes. The voltage. So the question is, wouldn't there be a voltage drop across the resistor? The answer is yes, there will be a voltage drop. Yes. But in a series connection, it still does not matter. No. It's a series connection will still be the same. So the half-wave rectifier or this clipper circuit, what we are talking about is this. This was that, this was the half-wave rectifier circuit. And we took the output across the resistor here. And what I'm saying is, whether the resistor is drawn first or whether it's drawn second, electrically speaking, the circuit would not be any different. It's still in series, so it does not matter. Yeah, it's the same circuit. Doesn't make any difference. Okay. Yes. V out and VO. Yeah, I should have done this. Let's stick with what they have given. So I'll draw blue and I'll draw blue. Okay. Does that clear up the confusion? Okay. I was just trying to illustrate a point saying that, in this example, we are taking the output across the diode, we still get a clipper circuit. If we take the output across the resistor, as we did in the lab, we still have a clipper circuit. Except the difference is this circuit, if we take VO across the diode, we obtain a positive clipper. The exact same circuit at the exact same time, if we take a second output across the resistor, we obtain a negative clip. Same circuit, two different outcomes. Right? So just something to think about, which would show up on the final exam. All right, other questions? What part? All of it? I said something like this could show up in the exam. I would say I'd have to go back and refer to the lecture video after I post it to realize what I just said. No, but I'm just saying that these are the possibilities. So something like this could show up in the final exam. Yeah. Sometimes students look at a circuit and say, "Good, this is something new. I never saw this before." And I just like to point out that yes, we have seen something like this before. Okay. All right. How about the next one with the battery? This again is something we did in the lab, right? Now we have flipped the direction of the diode as well as connected a battery in place. Why is, oh, there you go. So diode is flipped and we have a battery. And there are multiple combinations with this, right? I could have the diode pointing up. I could have the diode pointing down. I could have the anode connected to a positive battery terminal as shown here. I could have the cathode connected to the positive terminal. I could have the anode connected to a negative terminal. I could also have the cathode connected to a negative terminal. Multiple different possibilities, very interesting options. So let's see. Positive half cycle, what happens? We're applying a positive voltage at the input. First thing to do is to understand that the anode of the battery, anode of the diode is held at a specific potential, right? So the anode of the diode is held at plus 4 volts. Until and unless the cathode goes above 4 volts, the diode is not going to turn off, right? Assuming that the cathode is at 0, the anode is always at 4. If the anode is higher than the cathode, diode is always going to be on. The only time the diode turns off is if the cathode also goes above 4 volts. So if both are equal to 4, so if cathode is 4 volts or higher, then the diode turns off. So in the positive half cycle, if V in is less than 4 volts, diode is on. What is the output? We did this in the lab. If you wrote out an analysis of your results, you should be able to explain this. All right, let me draw it out. Right? Anode is at plus 4 volts, right? And we have the input cycle. So as long as the cathode is less than 4 volts, diode is on. Cathode goes above 4 volts, diode is off. So if you're applying V in, sinusoidal waveform, half wave of the positive cycle, as long as V in is less than 4 volts, diode is off. I'm sorry, diode is on. So if diode is on, it behaves like a short circuit. If diode is a short circuit, what is the voltage at the output? It's 4 volts. So when cathode is less than 4 volts, circuit looks like this. That 4 volts battery is directly connected to the output. So you obtain 4 volts. Okay. It's a flat line. So it's a flat line. Any input that you apply at that point is clipped, right? V out is 4 volts. So now let's ask this. What happens when cathode goes above 4 volts? Diode turns off. What is my output then? VO is equal to V in. So now let's say you have a waveform input. I want all of you to try and draw this. If I'm applying an input waveform that looks like this, let's just say this is, I don't know, 10 volts. Actually, let's make it easier. Let's do it 8 volts. So this is 4. So draw the output. I want everyone to try this. What do you think would be the output? Just for the positive half cycle. We'll talk about the negative later on, but just look at the positive cycle. So first thing to do with this the approach that you want to take for this kind of problem is look at the V in, right? What did we say? We are breaking up the V in 2 parts. First is the positive cycle, next is the negative cycle. Then in the positive cycle, we are further breaking it down into 2 parts when V in is less than 4 and V in is above 4. So first draw out the waveform for V in less than 4. Find the corresponding time point where V in is less than 4. So this would be here, right up to here. Up till this point, V in is less than 4. What is my output when V in is less than 4? So what do you all think should be line? Yeah, this is a flat line, right? On the right track. So you got a flat line. Somebody online, please send a message. So we will have a flat line at 4 volts. Does that make sense? Let's take a pause while you think over it. Let me know if you have any questions. Any questions at all? Does that make sense? Okay. All right. What happens after that? Then diode turns off. Diode turns off. Then V out simply follows V in. So I want to say, let's see, up to here. Okay, V out simply follows V in, because that's the point where V in again goes below 0. So now that you know this, and when V in goes below 0, output again is battery. And so all the way up to here is the result of our positive half cycle. Okay. Now, what happens in the negative half cycle? It flatlines. So because it's negative, diode is always on. If diode is always on, then the battery is connected there. So all the way to the negative half cycle, which is, let's say, up to this point, we obtain a flat line. Okay, we obtain a where. So after the negative half cycle, it will again follow the same shape. So you're talking about after this point. Yeah, so it'll follow the shape from the first one. So it'll go up to here, and then again it will turn on. So at that point, the cycle will just repeat. Yeah. So not quite a clipper, not quite a clamper. Okay. These kind of circuits collectively are known as diode wave shaping circuits. Okay, so these are known as wave shaping circuits. All right, diode wave shaping circuits. But almost 99% certain, similar problem will appear on the final exam. Okay, this could be any combination. Think about all the possible combinations. I could flip the battery. The battery flips, then we don't know when the diode conducts. You could take the output across the resistor, perhaps. We could have another resistor in series with the diode, take the output across that resistor, maybe. I don't know. But I'll expect with 99% certainty as of now that a similar problem will be on the final exam. Okay. All right, let's take a pause. Let me know if you have any other questions. All good. Okay. All right, one final is the clamper circuit. So diode clampers. Anyone want to take a crack at explaining this? We can still use the same ideal diode model. It helps to draw it out. So let me help you out. Let's say we have in the positive half cycle, we can represent the circuit like this. right? And the diode is going to be on. And that's VO. So what is VO? If it's ideal diode. 0 volts because it's a short, right? Ideal diode. So V out is equal to 0 volts. However, far more interesting is what happens to the capacitor. Again, this was part of lab 4, right? We saw that capacitor current flows this direction. Nothing would flow through the resistor because the diode is almost a short. Ideal diode, R is equal to 0. If it's a 0, output is short, that resistor is effectively removed from the circuit. All of the current goes to the capacitor and the diode. Capacitor charges with a plus on the left, minus on the right. What happens in the negative half? So we have a capacitor here that is fully charged. And diode is off. And you have resistance R. So the capacitor VC and V in, or V in by 2 to be more accurate, because it's the half cycle. So V out or VO is going to be VC plus V in by 2. Okay, VC plus V in by 2. But the polarity of V out is the opposite, right? It's taking the opposite. So it's minus and minus. So it'd be minus VC minus V in by 2 because it's the negative cycle. And so if I was to draw a waveform, and for simplicity's sake, instead of sine wave, let's go with square wave. If this is my V in, and I'm drawing V out. For the positive half cycle, I have 0. In the negative half cycle, it goes VC and this level here is VC plus V in by 2, minus of VC plus minus V in by 2. Yes. So when the capacitor charges, variation in what? You're talking about the transient portion? If it's a really, so the question, it's a very good point. Question being asked is, what about the transient portion when the capacitor is charging up? So the answer is the diode resistance is very, very small. So even in real life, the diode static resistance is going to be very small. So the capacitor can charge very quickly. It's probably not sufficient time. So if the frequency of our waveform was pretty high, meaning it's flipping very fast, then there's not enough time to actually notice that charge and discharge. So if we slowed down the frequency, if we reduce the frequency a whole lot and we slowed down the positive and negative half cycle, the flipping, and if the capacitor was a really large size, then we would observe that slope, which we actually did in the pre-lab as well as in the lab when we put in we put in a output load resistor that was far smaller. It discharged faster, so the slope was more pronounced when it's trying to discharge. So if it's, let me understand the question. If it's fully charged, it behaves like an open circuit. That's only if it's at steady state, if it's at DC steady state. So at that moment in time when it reaches full charge, that's when it behaves like an open circuit. Yes. Well, I mean, if we just analyze, so the question being asked is about this portion right here. For that small portion in time, it's effectively DC. So yes, once it reaches full charge, it behaves like an open circuit. But then after the positive half cycle, it flips to negative half cycle. And so now it's reversed. So if we really wanted to see the effects of the questions that are being asked, we could perform the experiment in the lab. We could create the clamper circuit. And if we applied a low enough frequency, let's say half a hertz or even a quarter hertz, which is possible with our function generators, we would see the effects that you're referring to, that there would be a slope in there because it's not charging fast enough, right? So we could increase the size of the capacitor and we could lower the frequency to less than 1 hertz, and we would be able to see a slope, like a charging and discharging, which is definitely possible. But the thing to keep in mind is that the time constant R times C. So to increase the time constant, we can increase the capacitor, size of the capacitor, but the R in charging is the diode resistance. We cannot increase that. The only way to increase it is by having multiple diodes in series. So if we have multiple diodes in series, then we could possibly increase the series resistance in there. That's the only way to observe that charging effect. But small capacitor with a small small in a voltage, a high in a frequency, it just flips too fast to make any noticeable difference. It's only when we actually go to discharge, that's where we are able to see the difference. So discharging occurs through the resistor. So discharge portion is now through the resistor. So V out will have a voltage like this. Actually, no. It's not confused. V out is measured like this, but the voltage drop created is like this. Okay. And so V out is minus VC plus V in over 2. Again, transient effects, if we wish to observe the transient effects, meaning the slope of the charging and discharging, then the capacitor must be large. And then during the charging portion, the diode must have a higher resistance. Then we can observe the transient portion. Okay. All right. Any other? Yes. The magnitude of what? Oh, I didn't put a value to it, but we can just say it's V in over 2, and here it's minus V in over 2. So I didn't put a specific number to it, but that's what it is. Just assuming that it's symmetrical above the horizontal axis. Okay. So question being asked is, would we see a similar behavior if we flip the diode? We'll find out in the final exam. That's a very good question. What happens if we flip the diode? It will clamp positive. So flip the diode, then it's charging in the negative half cycle versus the positive half cycle. And so instead of being a negative clamper, it would be now a positive clamp. Yeah. Okay. So these kind of clamper circuits are also part of the diode wave shaping family. Okay. So there are multiple variations on this. Flip and clamp is we are clamping the level of the voltage waveform. Either we are clamping it above or we're clamping it below. Yeah. One application of clamper circuits, we will see when we do amplifiers, BJT amplifiers. In BJT amplifiers, we apply a DC bias on the output side. We apply a small AC input signal. And so the transistor takes the DC energy and gives it the shape of the AC signal. So by default, the output of any amplifier will have a DC component along with the AC signal. So the AC signal it's not centered around 0. It's centered somewhere like, plus 5 volts or plus 8 volts or plus 10 volts. So at that point, we want to shift it down back to 0. That's where we would apply a clamper circuit. Okay. All right, that's the end of the diodes. Oh, one more point about clippers. In the lab, you did a procedure with back-to-back Zener diodes. What kind of circuit was it? It was a clipper circuit. You didn't did you remember the output you obtained? Two back-to-back Zener diodes conduct in both directions. So if the input waveform is larger than the breakdown of voltage of the Zener diode conducts, clips the rest of the circuitry. So you have a positive clipper and you have a negative clipper without using any power source. Those kind of circuits are used in voltage surge protectors. So if a surge comes in larger than 120 volts, it clips. Doesn't affect. The rest of it is not allowed to go through. Question? Okay. All right. So the next should be bipolar junction transistors, but there's a JFET experiment. So what I usually like to do is start with JFETs, field effect transistors. That should be chapter 5, chapter 4. In the book, I think it's like chapter 4. So don't worry about it. But the topic is about field effect transistors, FETs. There are three primary broad categories: junction FETs, known as JFETs, metal oxide semiconductor FETs, MOSFETs, and metal semiconductor FETs called MESFETs. And there's no misfits. Okay. So JFETs are not as widely used anymore. Okay. Most popular is, what's the most popular? MOSFETs. You've all heard that. Everything nowadays is built on MOSFET technology. Most popular, most common. Okay. We have both for the JFETs and the MOSFETs, we have N-type and P-type, N-channel or P-channel FETs. When you build a circuit using both N-channel and P-channel MOSFETs, we get what is known as CMOS. So P-channel MOSFETs are known as PMOS transistors. N-channel MOSFETs are known as NMOS transistors. If you have both on the same circuit at the same time perform complementary functions, it's known as complementary MOS or CMOS circuits. That's where the name comes from. Okay. But anyway, the JFET is something I do right around here because lab 6 is about JFET characteristics. Okay. So JFET is a 3-terminal device. It's a 3-terminal device that has 2 PN junctions, but those 2 PN junctions are not back to back. They are not a sandwich structure. Okay. In a BJT, a bipolar junction transistor, they are back to back structures. FET is a very different kind of fabrication structure. Okay. What we do in a FET, specifically a JFET, not a MOSFET, junction FET, if this is the top surface of my silicon substrate or silicon wafer, and I was creating a JFET device in there, from the top, it's going to look like this. Okay. And there is a embedded structure. Let's say this is P-type. And this is N-type. So the space in the middle is the channel that permits the carriers to flow through. In this case, if you have P-type material on either side, you have an N-type material in the middle. The structure is made out of N-type material, so the channel is N-type. Okay, this entire structure is made out of N-type material. Okay. One end of this device is known as the source. The other is known as the drain, D. Source, drain, and then we have a gate that controls the flow of carriers between the source and the drain. Okay. That was going to be my next question. What do you notice about the physical construction between the device on the left and the right? And the answer, as you said, is that the source and drain are interchangeable. It's a symmetrical device. If you fabricate it symmetrical fashion, which is JFET, then the source and the drain could be interchangeable. But in some devices, one of those could be tied to the body of the substrate, which is more common in MOSFETs, though. But if it's a JFET that's manufactured symmetrically, then the source and the drain could be interchangeable. So gate, source, and drain is a 3-terminal device. And we can see the symbol that's on the left here. So the arrow is pointing into the device. It's an N-channel N-channel JFET. And if the arrow is pointing out, it's a P-channel JFET. This arrow points in. It's an N-channel. And if the arrow points out, is a P-channel. Okay. P and N, again, from the fundamentals, simply holes versus electrons. But the symbol is, as you can see the symbol over here, we have one terminal that is common to both sides. So you have an input side and you have an output side. And then you could have, more often than not, it's the source. So you have the source and the gate forming the input, and the source and the drain forming the output. So you bias the JFET and you can take the output across the drain. I want to just quickly, actually, wait, did anybody have JFET experiment this week? You already done? Who's your instructor? Huh? Oh, okay. Okay, so you did BJTs. Okay. All right, now it makes a little more sense. All right, is 6 next week? Anyway, in my lab classes, we'll perform automated data collection using Sweep and Go. So once you set up the circuit correctly, you press a button, within 5 minutes, we'll be done. So it doesn't take too long. So I just want to show the characteristics right here. Transfer characteristics and output characteristics. On the input side, we have gate source voltage, VGS. And then on the output side, we have our drain current as a function of the drain source voltage, VDS. So on the input side, and we will look at this in detail after we look at the operation on Friday. On the input side, you have gate source voltage, VGS. On the output side, you have drain current ID. And the way it works is for FETs and for BJTs and for MOSFETs, you have on the input side, you change the input by 1 step. And on the output side, you sweep your voltage from, let's say, 0 to 10, 0 to 15, 0 to 20 volts. And then you observe your output voltage, or you collect your output, you collect your output current. Okay. So for instance, for this FET, we'd have VGS is equal to 0. And on the output side, we'd sweep from 0 to 10 volts. And then we have a plot of ID versus VDS. So we have one set of data for one value of VGS. Then VGS is stepped up to a different level. So either from 0 to 1 volt. And on the output side, we again have a set of data that goes from 0 to 16 volts. And then ID as a function of VDS. And so you have a set of curves that we obtain that look like this, that are shown here. Okay. Anyway, I was just trying to get through this just in case if anybody had FET experiments coming up this week, but it sounds like nobody does. So, all right, we'll end class here today. We'll pick up here on Friday. Actually, not here. We'll pick up here first. We'll pick up from here on Friday, and we'll look at the operation of JFETs. And then after that, a little bit of MOSFET, and then we'll get into BJTs next week. The most important topic. Okay. All right. Yes.